All right, 8.2 Circles and Ellipses, starting on page 178 of your notes packet. Recall from the previous section, in 8.1 we were looking at conic sections and we focused on the parabola, which is the first of the conic sections that we're discussing. The second is the circle and ellipse, and the circle is a special case of the ellipse. Okay, so if we're looking at an ellipse, first we have to kind of understand what it is. So let's draw an ellipse. Looks like a stretched out circle. It has a center and it has two foci. Focuses is pronounced foci, plural of focus. Okay, and our equation that we'll use is x minus h squared divided by a squared plus y minus k squared divided by b squared equals 1. It will always equal 1. Sometimes you have to divide to set it equal to 1. Or if our major axis is in the y direction instead of the x direction, then we kind of switch these. We have y minus k squared divided by a squared plus x minus h squared divided by b squared equals 1. And really, because addition is commutative, all we've done is we've changed the role of the variables a and b. Okay, our focal axis, now that's the axis where our foci lie, is y equals k or x equals h. Okay, and the equation for the actual point of each focus is h plus or minus some constant c, comma k, and h, comma k plus or minus that constant c. And we'll see where that variable c comes from. Okay, moving down here on our table, let's see if I can keep it all in frame. Our vertices, now the vertices are the points on the ends of the ellipse. So that's going to be h plus or minus a comma k and h comma k plus or minus a, where our semi-major axis is a and our semi-minor axis is b. Semi meaning half. So if this whole axis is the major axis, then a is half of it, just from the center to the vertex. And we have this Pythagorean relation, a squared equals b squared plus c squared, which holds true for both ellipse, both shapes of our ellipse. Now, the reason this isn't the standard Pythagorean relation that we're used to seeing is because what these variables represent, a is the major axis. It's the longest part of our ellipse. So a is actually the longest piece of this relation. So if we're looking at this Pythagorean relation and we draw our axes here through our ellipse, okay, now this distance from the center to the focus, this distance is c. The distance from the center to the vertex is a, and the distance from the center to the other side of our ellipse is b. So we end up, if we arrange a, b, and c into a triangle, a is the longest side, then we have b, and we have c is the shorter side. So a would be the hypotenuse between b and c. So a, b, c. And that's where this Pythagorean relation comes from. If you look below, there's a diagram that shows both shapes of ellipse, one with a horizontal major axis and one with a vertical major axis. On the next page, example 1 says find the vertices and the foci of the ellipse given. Okay, now notice this is not set equal to 1, so that should be our first step. So if we divide everything by 36, 4 divided by 36 is 1/9. We have 9 left in the denominator, so we have x squared divided by 9 plus, reducing similarly, y squared over 4 equals 1. Okay, now 9 is greater than 4, so I know I have a horizontal ellipse. Okay, now I've exaggerated it. So we have that a squared equals 9 and b squared equals 4. So A is 3 and B is 2. Now what this means is that from the center, if I were to draw this, notice that I don't have anything subtracted from x or y. So my center is 0, 0. My A value would mean 1, 2, 3. That's my vertex. 1, 2, 3. There's another vertex. And then the B value means 1, 2, 1, 2. Okay, so as you can see, I've exaggerated it. My X value is much more spaced out than my Y axis. Okay, so my vertices I can find are 3 and negative 3 comma 0. So plus or minus 3 comma 0. And now the foci I have to calculate. I have to calculate my value for C, right? And remember, A is our largest one. So C, we'll just start with the basic formula. A squared equals B squared plus C squared. So I have 9 equals 4 plus C squared. Well, 4 plus what? So C squared equals 5. So C is plus or minus the square root of 5. So that means my foci are at plus or minus the square root of 5 comma 0. So here are my answers. We have, oh, it didn't ask for the center. So just the vertices and the foci. Now, because of that plus or minus, those are actually two different points. So if you wanted to list them, you could say that your vertices are at 3, 0 and negative 3, 0, and then your foci are at square root of 5 comma 0 and negative square root of 5 comma 0. All right, moving on to example 2. We want to, our objective is to graph ellipses, and we looked at that a little bit in example 1. So we want to find an equation of an ellipse with a foci at 0, negative 3 and 0, 3, whose minor axis has a length of 4. Okay, so I'm going to start by graphing the foci. So 0, negative 3, 1, 2, 3, and 0, 3. And a minor axis goes in the opposite direction as the foci. So it has a length of 4, which means 2 on either side of the focal axis. So I already know that my ellipse is going to go through these 2 points on my x-axis, but it doesn't go through the foci, it goes around the foci. So we want to sketch the ellipse and support the sketch with a grapher. And we need to find out where our vertices are. So A squared equals B squared plus C squared. Okay, A is unknown, but we do know B and C. So if our foci are at these points, then our value for C is 3, and our value for B is 2. So A squared equals 4 plus 9, which is 13. So A equals plus or minus the square root of 13. Now we choose the positive. So A is the square root of 13. If you choose the negative, you'll just have your vertices backwards. It doesn't matter. They're both vertices. Okay. So square root of 13 is the point 0 comma square root of 13 and 0 comma negative square root of 13 is the point that goes on the ellipse, our 2 vertices. Okay, so find the equation of the ellipse. We need to find the equation. So if our major axis is the y, then and our center is at 0, 0, then we have y squared divided by a squared plus x squared divided by b squared equals 1. So this is our equation of the ellipse. Okay. To put this onto a graphing utility, you would have to solve for y. So onto a graphing utility, we would have y squared divided by 13 equals 1 minus x squared over 4. Multiplying by 13, y squared equals 13 times the quantity of 1 minus x squared over 4. So then we would have the 2 equations, y equals plus or minus the square root of 13 times the quantity of 1 minus x squared over 4. And if we put that into our graphing calculator, we get this ellipse. Now, Where those two equations meet, the graphing calculator is not exact. They should actually meet up, and if you zoom in, you'll see that they do. Okay, so even though it looks like there's a gap from this view, if you zoom in, you can tell that they actually do go up to meet at the x-axis. So that is one of the things that you should know about when you graph these on your calculator. Example 3 is similar to what we just did in example 2, and example 4 asks to find the center, vertices, and foci of the ellipse. So do example 3 and 4 on your own. All right, after example 4, we're looking at the eccentricity of an ellipse. So eccentricity is defined as E equals C over A. And by substituting in the value of C from our Pythagorean theorem before, our Pythagorean identity, we can get the square root of A squared minus B squared divided by A. Okay, where A, just as we defined before, is the semi-major axis, B is the semi-minor axis, C is the distance from the center of the ellipse to the focus. Ellipse. To either focus. To see what this means, we're going to look at the Earth. Now, the Earth does not travel in a perfect circle. It travels around the sun in an ellipse, and the sun is actually not in the center, it's at the focus. So the way that we're going to look at eccentricity here is to see how kind of skewed is the Earth's path around the sun. That's kind of what it means. Okay, so Earth's orbit has a semi-major axis, A, about 149.598 gigameters, and an eccentricity of approximately 0.0167. So we want to calculate and interpret our B and C, our semi-minor axis, and our focal distance. Okay, so I can start with the equation E equals C over A, and then rewrite this so that I know E is 0.0167, and I know that A, I'll put a little arrow because I'm filling in values, I'm substituting values, equals C divided by 149.598. So if I multiply the denominator on both sides, I find that C has a value of 2.498286. Now using the Pythagorean identity, we can find that B equals the square root of A squared minus C squared. Remember, A squared equals B squared plus C squared in this case. So I can fill in those values. 149.598 squared minus 2.498286 squared. So I have a B value of 149.577. Okay, so now we have A, B, C, and E. And what this tells us, now we're interpreting this, notice that our minor axis, our semi-minor axis, is very, very close to our semi-major axis. So the Earth's orbit is nearly circular. Now these are in gigameters, so even though they're very close, there's actually a pretty big distance difference if we were measuring in meters, but with the scale of the Earth orbiting the sun, it's very nearly circular. But the sun is at the focus, so the sun is not at the center. It is at a focus. And since C is very small, we know that that's pretty close to the center. So if we're looking, actually, let's draw this a little bit more to scale. So it's kind of like this, a little bit longer in one direction. Here's our center and our foci. So here is, we'll just circle this one, is the sun, and here would be the Earth. All right, on the next page, looking at example 6, I'll help set this up and then you'll take it from there. So a lithotripter is used to break up kidney stones. And what we want to do is we want to calculate the ellipse that's used, the ellipsoid, so ellipse-shaped object, that's used in the lithotripter, and it has a major axis of 12 feet and a minor axis of 5 feet. So if we were to draw this, and it doesn't really matter which direction we draw in, but we'll just do something like this. So if its major axis is 6 feet, that means, or 12 feet, that means it's 6 feet on either side. And its minor axis is 5 feet, which means it's 2.5 feet on either side. Okay, how far from the center are the foci? So we're looking for what is C. Here's my drawing. Okay, we'll pretend that looks like an ellipse. So this value would give us that A is 6. This point here gives us that B is 2.5, and we're looking for C. All right, I'll leave the rest up to you. All right, our last example for this section, example 7, we want to solve the system of equations. Now remember, when solving a system of equations, we're looking for the points that intersect. Looking for intersection. Okay, so looking at this first equation looks like an ellipse, and this second equation looks like a parabola. So let's start with the ellipse. I need to set it equal to 1, so dividing everything by 4. X squared divided by 4 plus y squared, I'll put it over 1 for the sake of consistency, equals 1. So I know that 4 is greater than 1, so my A is 2. A squared was 4, so A is 2. B is 1. So I end up with an ellipse that looks something like, A is in the direction of X, 1, 2, 1, 2, 1, 1. Here is my ellipse. Okay, and then we have a parabola, y equals 2x squared minus 3. And I can confirm this with a graphing calculator. It is indeed a parabola. And this is an ellipse. And the parabola has a y-intercept at -3. And it's stretched by 2. So I know that it's going to go through, the point 2 up, 1 over. So it's going to be slightly below our ellipse here. Okay. So it goes like this, and there is our parabola. Now to find these exact intersection points, we can use our graphing calculator. The parabola is pretty straightforward. In y1, I'll put 2x squared minus 3. Okay, but as usual for the ellipse, we need to solve it into implicit form. So this will be y equals, luckily it's just divided by 1, so we just need to subtract over and take the square root. So plus or minus the square root of 1 minus x squared over 4. Now when typing this into your calculator, make sure you include parentheses around that. So we have the square root of 1 minus x squared over 4 and negative square root of 1 minus x squared over 4. So those are my equations there. And then I hit graph. Let's see what it comes up with. There's our parabola. There's our top half and bottom half of our ellipse. I'm going to go ahead and zoom in so that we can get a little bit of a better look here. And there we go. So what I want to do now is I want to calculate the point of intersection. Second, calculate. Option 5 is intersection. It's going to take first and second curve. Now remember, there are 3 curves on here. So let's see if I can find my cursor there. I'll find this one first. Okay, so my first curve, enter. Second curve, it's already very close, so I know it's on the right curve. Enter, and then my guess, enter. So that point of intersection, it tells me this point right here is negative 1.04, comma, negative 0.86, okay? Because of symmetry in both shapes, I know that this point here will then be 1.04, comma, negative 0.86. However, a parabola does not have symmetry over a second axis. So I cannot say the same thing about the last 2 points. And this drawing is definitely not to scale because you can see that those points don't look symmetrical. Okay, but those 2 points should look symmetric. So again, calculate the point of intersection. Let's go up to here, enter. It looks like it's on the right curve. Whoops. Enter, guess, enter. If you do need to go between curves, you use the up and down arrows, whereas to travel along the curve, you use the left and right arrows. All right, so my new point of intersection, negative 1.37, comma, 0.73, which means that this point over here is 1.37, comma, 0.73. All right, so those are my 4 points of intersection, or the 4 solutions to my system of equations. Go ahead and think about what you learned from this lesson and summarize it in the box below.